Black holes sit at the edge of what we can see and what we can measure. They pull in light, matter, and our questions. When a massive star runs out of fuel, its core can no longer support the weight above it. Gravity then wins, and the core collapses inward. I find it hard to picture a star's heart crushing itself into something smaller than a city. The collapse continues until nothing can halt the inward pull. At that point, the object becomes a black hole. Its outer boundary is called the event horizon. Anything crossing that line cannot escape, not even light. The horizon is not a solid surface. It is a one-way membrane in space-time. Inside the horizon, the equations of general relativity predict a singularity. That is a point where density and curvature become infinite. We do not really know what physics looks like there. The singularity is a mathematical placeholder, not a description we can test. The first hints of such objects came in the 18th century. John Michell imagined dark stars whose gravity was strong enough to trap light. Around the same time, Pierre-Simon Laplace wrote a similar idea. Those thoughts were speculative, but they showed that gravity could be extreme. A century later, Carl Schwarzschild solved Einstein's field equations for a spherical mass. His solution described a radius where escape velocity equals the speed of light. That radius is what we now call the Schwarzschild radius, the size of the event horizon for a non-spinning black hole. In the 1930s, Oppenheimer and Snyder modeled the collapse of a massive star. Their work showed that, under realistic conditions, a star could indeed form an event horizon. It was a theoretical proof that black holes could exist in nature. The term black hole itself was coined much later in the 1960s by journalist John Wheeler. By then, radio astronomers had found mysterious X-ray sources. One of them, Cygnus X1, behaved like a compact object devouring a companion star. Its mass was too high for a neutron star, so many concluded it was a stellar mass black hole. Stellar mass black holes are the remnants of stars at least about 20 times the Sun's mass. Their horizons span a few tens of kilometers, roughly the size of a small town. Despite that tiny size, they can contain more mass than 1,000,000 suns. At the centers of most galaxies, we find far larger black holes. These supermassive black holes can weigh billions of solar masses. Their horizons stretch across millions of kilometers, comparable to the orbit of Mercury. How they grew so massive is still a matter of research. There is also an intermediate class, with masses between 100 and 100,000 suns. They are harder to spot, but a few candidates have emerged from surveys of dwarf galaxies. Their existence hints that black holes may form through multiple pathways. Observational breakthroughs arrived in the last decade. In 2015, the LIGO detectors heard ripples in space-time from two merging black holes. The signal matched predictions from general relativity, confirming that black holes can collide. A year later, the Event Horizon Telescope combined radio dishes across the globe to image the shadow of the black hole in galaxy M87. The picture showed a dark circle surrounded by a bright ring of hot gas. It was the first direct glimpse of an event horizon's outline. These observations do not answer every question. We still do not know what happens at the singularity or how quantum effects might modify it. Theories such as Hawking radiation suggest black holes could slowly evaporate, but the effect is too weak to measure for any known hole. Why do scientists keep returning to these objects? Part of the appeal is that black holes sit at the intersection of gravity, quantum physics, and high-energy astrophysics. They force our theories to stretch, sometimes to the breaking point. They also act as natural laboratories. Matter falling toward a black hole heats up, emitting X-rays that we can detect. By studying those signals, we infer the spin, mass, and environment of the hole. The spin tells us how the black hole was built. A rapidly rotating hole likely grew by accreting gas over long periods. A slower spin could indicate a merger of smaller holes. These clues help reconstruct the history of galaxies. Even though black holes are extreme, they are not immediate threats to Earth. The nearest known black hole, V616 Mon, lies about 3,000 light-years away. Its gravitational influence on the solar system is negligible. Nevertheless, the concept of a black hole swallowing the Sun or the Earth captures the imagination. In reality, a star would have to wander very close, within a few hundred kilometers, to be captured. The odds of that happening are astronomically low. Our understanding of black holes rests on a combination of theory, observation, and a willingness to accept that some answers may stay hidden. Each new measurement refines the picture, but also reveals fresh gaps. When I look at the faint X-ray flicker from a distant binary system, I am reminded that something invisible is pulling at the gas. The light that finally escapes carries the imprint of a horizon we cannot touch. The quiet hum of a detector, the faint glow of an accretion disk, these are the only signs we have of an object that lets nothing out. It is a strange paradox that we learn about the darkest places by the light they deny. In the end, black holes remain both a puzzle and a tool. They test the limits of our equations, and they illuminate the dynamics of galaxies. A single photon, skimming the edge of an event horizon, can linger for milliseconds before slipping forever inward. That brief pause is the only moment we can claim to have witnessed the abyss. Stellar mass black holes sit at the low end of the scale, typically weighing 5 to 20 times the Sun's mass. Their event horizons are only a few dozen kilometers across, about the size of a small city, yet they carry the same gravitational pull that once held a massive star together. I find it hard to picture how something so compact can swallow light, but the math is unforgiving. Each solar mass adds roughly 3 kilometers to the radius. When a star much larger than the Sun collapses, the result can be a black hole of 100 solar masses or more. That pushes us into the realm of intermediate mass objects, a class that still feels almost speculative. Their horizons stretch from a few hundred kilometers to several thousand, enough to eclipse a mountain range. Observations suggest they are far scarcer than their lighter cousins. Only a handful have been identified in nearby galaxies, and even those detections sit on the edge of our instrument's sensitivity. At the opposite extreme sit the supermassive black holes, whose masses range from 1 million to 10 billion suns. Their horizons can span millions of kilometers, comparable to the orbit of Mercury in our own system. Almost every large galaxy hosts one at its center, a fact that emerged from surveys of galactic nuclei rather than from a single, dramatic discovery. The sheer weight of these giants makes them dominate the dynamics of their host galaxies, pulling stars and gas into slow, graceful spirals. The mass-radius relationship is linear. Double the mass, double the radius. That simplicity masks a deeper truth. A 10 solar mass black hole has an event horizon about 30 kilometers wide. A 1 million solar mass counterpart expands to 3 million kilometers. The proportionality lets us translate a number in solar masses directly into a physical size, a handy shortcut when we try to compare objects that differ by orders of magnitude. Distribution across a typical spiral galaxy reflects this hierarchy. Hundreds of millions of stellar mass black holes likely wander the disk, remnants of countless supernovae over billions of years. Intermediate mass black holes, if they exist in significant numbers, would be scattered in dense star clusters, perhaps the remnants of runaway collisions. The supermassive resident, however, sits in the galactic bulge, anchored by the surrounding mass and by the galaxy's own evolution. We don't really know why intermediate mass black holes are so elusive. Some theories propose they form in the same way as their lighter siblings, but the required conditions, extremely dense clusters and prolonged mergers, are rare. Others suggest they grow from the seeds of early universe black holes, later swallowed by the growing supermassive giants. The lack of a clear population makes the middle of the scale feel like a missing link rather than a bridge. Even the term black hole can be misleading. It suggests a void, yet each class exerts a pressure on surrounding space that can be measured in the motion of nearby stars or gas. For stellar mass objects, the influence is local, detectable only within a few light years. Supermassive black holes, by contrast, shape the orbits of stars across entire galactic cores, their gravity felt over tens of thousands of light years. The prevalence of each type also informs how we think about potential hazards. A wandering stellar mass black hole passing near the solar system would need to come within a few astronomical units to perturb planetary orbits, a scenario that, statistically, is exceedingly unlikely. Intermediate mass black holes, if they existed in the halo, could pose a slightly larger risk, but their scarcity keeps the odds low. Supermassive black holes, anchored at galactic centers, are far removed from our neighborhood, their influence felt only through the slow drift of the Milky Way itself. Mass alone does not tell the whole story. Spin adds another dimension. A rapidly rotating black hole can drag spacetime around it, extending the region where objects feel its pull. Measurements of spin for supermassive black holes show a wide spread, hinting at diverse growth histories. For the smaller classes, spin estimates are harder to obtain, and the data remain patchy. I don't quite grasp how much spin changes the effective size, but the equations suggest a modest increase in the horizon for a maximally rotating case. The sheer range, from a few kilometers to billions of kilometers, makes black holes a unique laboratory for testing gravity. The same equations that predict the event horizon apply across the entire spectrum, offering a single framework that embraces objects as different as a stellar remnant and a galactic nucleus. This continuity is comforting, even when the underlying physics pushes us to the limits of what we can observe. In practice, astronomers locate stellar mass black holes by spotting X-ray binaries, where a companion star feeds material into an accretion disk. Intermediate mass candidates emerge from unusual ultraluminous X-ray sources, though alternative explanations often compete. Supermassive black holes reveal themselves through the motion of stars near galactic centers or through the emission of active galactic nuclei. Each method reflects the scale at which the black hole interacts with its environment. The rarity of intermediate mass black holes keeps them from dominating any galaxy's center, yet they could serve as stepping stones in the growth of supermassive giants. Some simulations show a cascade of mergers, where several hundred solar mass objects coalesce into a million solar mass seed, later fed by gas inflows. The picture is still sketchy, and the data are thin, but the idea fits the observed distribution of the other two classes. When we compare the numbers, a typical galaxy might contain a few hundred million stellar mass black holes, a handful of intermediate mass ones, and one supermassive resident. That disparity underscores how the universe builds structure. Many small pieces, few middle pieces, a single massive anchor. The pattern echoes other astrophysical hierarchies, yet the black holes themselves remain the most extreme examples. If you look at the event horizon of a 10 solar mass black hole, it would fit inside a coffee cup. The same horizon for a 10 million solar mass black hole would stretch beyond the orbit of Mercury. That contrast, measured in everyday terms, is the clearest reminder of how diverse these objects truly are. The nearest black hole we can point to with confidence is Gaia BH1, a quiet, invisible companion to a sun-like star about 1/600 light-years away. It was uncovered not by a burst of radiation, but by the wobble it forces on its partner, tiny shifts in the star's position measured over years by the Gaia spacecraft. That wobble is a kind of laboratory note. The star drifts a few milliarcseconds, a motion that would be invisible without the precise astrometry we now possess. Gaia BH1 is a stellar mass black hole, roughly 9 times the mass of our Sun. In astronomical units, it sits roughly 100 AU from the Sun, far beyond the Oort cloud, far beyond the Kuiper belt, far beyond any planet we know. At that distance, its gravity is comparable to the tug of a passing star moving at a few kilometers per second. The solar system feels it as a faint tide, barely enough to nudge comets that already wander at the edge of the Sun's sphere of influence. A handful of other black holes linger within a few thousand light years. The system V616 Mon, also called A062000, is a binary where a black hole of about 6 solar masses siphons gas from a low-mass companion. It sits roughly 30 light-years from us, its X-ray outbursts flashing every few decades. Those outbursts are brief, lasting weeks to months, and the emitted radiation dilutes to a whisper by the time it reaches Earth. The gravitational pull at our distance is still minuscule, on the order of 10 ms2, a fraction of the Sun's pull on the Earth. Microlensing surveys have added a few more candidates. When a massive object passes directly between a distant star and us, the star's light brightens for a short time. In 2022, a microlensing event labeled Ogle 2011 BLG0462 hinted at a black hole roughly 50 light-years away, mass around 7 m. The event lasted a few weeks, and the derived trajectory suggests the black hole drifts through the galactic disk at about 30 km/s. Its path never brings it closer than a few hundred parsecs to the Sun, so its tidal influence stays well below the level that would disturb planetary orbits. The orbital dynamics of nearby stars give us another way to sense hidden mass. Stars in the solar neighborhood move in a smooth flow, but a few show slight deviations, small accelerations that cannot be explained by visible companions. One such star, HD 164509, exhibits a proper motion anomaly that matches the presence of an unseen 4 solar mass object at roughly 20 AU from the star itself. That object is likely a black hole, but even if it were a rogue planet, its pull on the Sun would be negligible. Gravitational perturbations from these nearby black holes are, in practice, dwarfed by the collective pull of the Milky Way's disk and halo. The galaxy's mass distribution creates a background field that sets the overall trajectory of the solar system around the galactic center. A single black hole, unless it wanders within a few tens of AU, cannot alter that motion in any measurable way. The safety margin we talk about, often quoted as a few thousand astronomical units, is not a hard wall but a statistical buffer derived from the density of known black holes and the typical velocities they carry. We do have to admit a limitation here. The census of black holes within a few thousand light-years is incomplete. Many black holes are truly dark, emitting no X-rays, no radio, no visible companion. Their existence is inferred only when they happen to cross the line of sight to a background star, an event that is rare and hard to predict. The current sample of about a dozen candidates may represent only a fraction of the true population. Even with that uncertainty, the odds of a black hole entering the inner solar system in any human timescale are vanishingly small. To bring a black hole within, say, 10 AU of the Sun would require a close encounter with a star that itself passes within that distance, a scenario that would have left a clear imprint on the orbits of the outer planets. No such imprint exists. The detection methods we rely on, microlensing, X-ray binaries, astrometric wobbles, each have a bias towards certain kinds of systems. Microlensing favors isolated black holes, but only when they align with a bright background source. X-ray binaries reveal black holes that are actively feeding, yet most black holes are quiet. Astrometry can catch the subtle dance of a star and its invisible partner, but only for nearby systems where Gaia's precision is sufficient. Because of these biases, we may be missing a population of black holes that are both nearby and truly dormant. If a dormant black hole were to drift closer, the first sign would likely be a tiny change in the motion of a well-studied star. Astronomers would notice a discrepancy in the proper motion data, perhaps a shift of a few micro-arcseconds per year. That would trigger a cascade of follow-up observations, radial velocity checks, high-resolution imaging, perhaps a search for faint X-ray emission. Until such a signal appears, the solar system continues its quiet orbit, feeling only the faint, distant tug of these unseen neighbors. One of the more precise measurements we have today comes from the Gaia Catalog's parallax of the star LHS 102, which sits about 12 light-years away. Its distance is known to within a few thousandths of a parsec, and its motion shows no unexplained acceleration. That absence of a wobble tells us there is no massive, unseen companion lurking within a few hundred AU of it. In the same way, the lack of any detectable acceleration in the Sun's motion relative to the barycenter of the solar system tells us we are not being nudged by a hidden black hole any closer than the Oort cloud. The quiet is almost reassuring. Yet I find it hard to picture a black hole drifting silently through the interstellar medium, its gravity stretching space like a slow, invisible tide. The notion feels both concrete. Gravity is a force we can measure, and abstract, an object we cannot see, only infer. It doesn't quite make sense when you try to imagine the black hole's event horizon as a sphere of nothingness moving through the galaxy, leaving only a faint ripple in the motions of distant stars. At the edge of the local bubble, a faint X-ray source flickers for a few seconds each year, cataloged as 4U154347. Its position aligns with a known binary system, but the exact nature of the compact object remains debated. If it proves to be a black hole, it would sit about 2,500 light-years away, its influence still a whisper on the scale of our planetary system. So far, the Neighborhood Watch finds only distant silhouettes, black holes that sit far enough away that their gravity is a gentle, almost negligible pressure on the solar system's outer reaches. The most immediate concern remains the ordinary stars and interstellar clouds that we can see, not the silent, dark remnants that drift in the background. A faint proper motion vector for the star Ross 128, measured last month, shows a tiny deviation of 0.03 mas, or that some models attribute to a low-mass object at roughly 1/500 AU. The data are still noisy, but if that deviation holds, it could be the first hint of a nearby, non-luminous companion, perhaps a black hole, perhaps something else. The observation sits on a single line of a data table, a tiny number waiting for confirmation. The center of our galaxy hides a dark mass that refuses to shine. Sagittarius A sits roughly 24,000 light-years from the Sun, its presence inferred from the swift dance of nearby stars. Those stars, especially the famous S2, trace tight ellipses that betray a central weight of about 4 million times the Sun's mass. I record the numbers, then stare at the empty space they describe, and I find it hard to picture how such a compact object can hold that much gravity without a surface to touch. A black hole of that size is called supermassive, a term that sounds grand but is just a label for the mass. Its event horizon, the point of no return, spans about 12 million kilometers, a sphere that would swallow Earth whole if it were placed at the Sun's distance. Yet we sit comfortably at a distance where the horizon is a speck in the night sky, invisible even to our most powerful telescopes. The gravity we feel from it is a whisper compared with the pull of the Milky Way's disk. The galaxy spins around the center in roughly 200 million years. Our solar system follows that rotation, completing a full circuit in a time that dwarfs human history. In that orbit we remain at a stable radius, never drifting inward enough for Sagittarius A* to dominate our local dynamics. The orbital speed of the Sun, about 200 kilometers per second, is set by the combined mass of stars, gas, dark matter, and the central black hole. The black hole contributes only a few percent of the total mass inside our orbit, so its effect on the Sun's path is modest. When material drifts close to the black hole, it heats and emits radiation. Sagittarius A* is currently quiet, with only occasional flares in the X-ray and infrared bands. Those flares last minutes, rising 100-fold before fading. I note the flare rate, perhaps once a day, sometimes less, then wonder whether such activity could ever reach us. The energy released spreads outward, diluted by the square of the distance, and by the time it arrives at Earth, it is indistinguishable from the background glow of the galaxy. Tidal forces near a black hole stretch objects along the line toward the center. The strength of that stretch falls off with the cube of the distance. At the radius of the Sun's orbit, the tidal gradient from Sagittarius A* is about 10⁹ times weaker than the tidal pull the Moon exerts on Earth. In other words, the black hole's tides are negligible for us. I write the numbers down, then shrug. Our oceans will not be ripped apart by a distant singularity. Evidence suggests that Sagittarius A* was not always so quiet. The Fermi satellite revealed gigantic lobes of high-energy particles extending above and below the galactic plane, the so-called Fermi bubbles. Their size, tens of thousands of light years, implies a powerful injection of energy a few million years ago. Some models attribute that burst to a period of rapid accretion onto the central black hole, a brief feeding frenzy that lit up the center. I record the age estimate, then acknowledge the uncertainty. We don't really know the exact cause of those bubbles. If a future feeding episode were to occur, the increase in radiation would still be far from lethal at Earth's distance. Even a 10-fold rise in X-ray output would be dwarfed by the Sun's constant emission. The main danger from a black hole, in theory, comes not from light but from a close encounter, an object passing within a few hundred astronomical units. Such a passerby would have to be on a trajectory that brings it deep into the inner halo, a scenario that simulations show is exceedingly rare. The Milky Way's halo contains many wandering stars and remnants, but their velocities keep them on wide, loosely bound orbits. The probability that one will plunge toward the center and then swing outward toward the Sun is minuscule. I add a note. The chance of a direct gravitational perturbation from Sagittarius A* is lower than the odds of a comet from the Oort cloud striking Earth in a given millennium. Gravitational waves, ripples in spacetime produced by massive mergers, travel outward at the speed of light. If Sagittarius A were to merge with another supermassive black hole, the wave burst would be detectable across the universe. Yet the energy carried by those waves would pass through Earth without leaving a permanent imprint. The only measurable effect would be a fleeting distortion of distances, far below any practical concern. The black hole's influence on the solar system can be expressed as a tiny correction to the Sun's motion. Precise astrometric data from missions like Gaia allow us to detect that correction, but it is at the level of micro-arcseconds per year, far beyond anything that could destabilize planetary orbits. I jot down the figure, then pause. The numbers are precise, but the practical impact is essentially zero. One might wonder whether the black hole could affect the flow of interstellar gas that eventually becomes part of new stars. The central region does host a dense cloud of molecular material, and its dynamics are shaped partly by the black hole's gravity. However, the gas that forms the Sun originated in a spiral arm far from the center, and the pathways that bring gas inward are complex, involving bar structures and turbulence. The black hole is a participant, not a director, in that process. Observations of nearby galaxies show that supermassive black holes can drive outflows that regulate star formation on galactic scales. In the Milky Way, the current outflow is weak, and the star-forming regions in the disk continue largely unaffected. I note the contrast with active galaxies, then return to our own quiet center. The distance between Earth and Sagittarius A also sets a limit on any potential gravitational lensing effect. Light from distant quasars passing near the black hole can be bent, creating multiple images. From our position, the angular deflection is minute, on the order of a few micro-arcseconds, and does not alter the appearance of the night sky in any noticeable way. I write the angular size, then acknowledge that it is essentially invisible to the naked eye. Even the notion of a black hole apocalypse feels misplaced when the numbers are laid out. The gravitational sphere of influence, defined where the black hole's mass dominates over the surrounding stars, extends only a few parsecs. The Sun lies well outside that sphere, comfortably within the realm where the collective mass of the galaxy governs motion. I record the radius, then note that it is a tiny fraction of the distance to us. If we were to imagine a future where the black hole awakens, the first sign would be an increase in radio and X-ray flares, detectable by observatories already in operation. The increase would be gradual, giving astronomers time to study the change. There is no mechanism for those flares to propagate as a destructive front. They are emissions, not forces that push matter outward. In the quiet of a night at the observatory, I stare at the radio map of the galactic center. The bright spot at the center is Sagittarius A, a point of radio intensity barely larger than a grain of sand on a photograph. Its faint glow reminds me that despite its mass, it is a distant, almost indifferent presence. The map shows a faint filament extending outward, a relic of past activity, curling like a thin thread in an otherwise dark tapestry. That filament, barely a few light years across, is the only concrete reminder that the center has once spoken louder than it does now. The first time LIGO's laser arms trembled, we recorded a ripple that matched the signature of two black holes spiraling together. It was a quiet proof that the universe can shake us without a single photon. When two black holes orbit each other, they lose orbital energy by emitting gravitational waves, tiny ripples in spacetime that spread outward at light speed. The loss forces the pair to draw closer, the orbit quickens, and in a fraction of a second the horizons merge into a single, larger whole. GW 150914, the event captured in September 2015, showed a chirp that rose from a few tens of hertz to a few hundred before vanishing. The detectors measured a strain of roughly 10-2, a displacement smaller than a proton's width across a 4-kilometer arm. The merger converted about 3 solar masses into pure gravitational radiation. That amount of energy, released in less than a second, outshines the combined light of all the stars in the observable universe for a brief instant. I find it hard to picture how mass can disappear so completely, yet the equations demand it. In more familiar terms, a supernova releases roughly 1 solar mass as light and particles. A black hole coalescence emits several times that amount, but in a form that barely interacts with matter. The waves pass through planets, rocks, even the vacuum, leaving only a fleeting stretch and squeeze. Because the wave's amplitude falls off with distance, the strain measured at Earth drops as 1 over the radius. A merger a billion light-years away still registers, but a comparable event 1,000 light-years away would produce a strain 1,000,000 times larger, still far below anything that could crack a rock. Even a strain of 10 would stretch a kilometer-long rod by 1/10 of a nanometer, an effect indistinguishable from thermal noise. The forces on Earth's crust, oceans, or atmosphere would be negligible. The planet would not feel a tremor, nor would the orbits of satellites be altered. Estimates based on LIGO's observing runs suggest a few dozen stellar mass black hole mergers per cubic gigaparsec per year. Translating that to our galactic neighborhood means a merger within a few hundred light-years is exceedingly rare. Perhaps once every many millions of years, if at all. For a merger to endanger Earth, it would need to occur within a few light-years, close enough that the strain approaches 10 or larger. No known black holes reside that close, and the Milky Way's population of stellar mass black holes is spread thinly across the disk. The odds of a dangerous event happening in our lifetime are essentially zero. Supermassive black holes at galaxy centers do merge, but those collisions involve masses millions of times larger and emit waves at far lower frequencies. Their mergers take place billions of light-years away, and the resulting strain at Earth is orders of magnitude smaller than that from a stellar mass event. They pose no direct threat. We still lack precise statistics for the nearest possible mergers. The detectors have only been listening for a handful of years. It doesn't quite make sense when you say, "We don't really know," and then try to assign a number. The uncertainty reminds us that our picture remains incomplete. When the latest signal passed through the interferometer, the photodiodes registered a minute change in light intensity, a whisper that the mirrors felt as a nanometer scale shift. The instrument's vacuum chambers, chilled to near absolute zero, recorded the passage without a single spark or sound. In the quiet of the lab, the data stream showed a single point where the waveform peaked, then fell silent, leaving a faint, lingering echo in the noise floor, a reminder that space can ripple even when we cannot feel it. I sit with the data like a quiet ledger, noting that black holes need not be glued to galactic cores. Some of them break free, wandering the void after a violent birth. When a massive star collapses, the core can receive a kick, a recoil from asymmetrical neutrino emission or from the merger that formed it. That kick can be hundreds of kilometers per second, enough to escape the shallow pull of a dwarf galaxy or to drift far from a larger spiral's disk. I write that these are the rogue black holes, solitary and fast, moving through interstellar space like cold, invisible bullets. The formation pathways are few but clear. A supernova that fails to eject all its envelope can leave a compact remnant with a net momentum. In a binary system, when one star collapses, the loss of mass can unbind the pair. The survivor and the newborn whole fling apart. In rare cases, two black holes merge, and the final wave emission carries away linear momentum, giving the merged object a recoil. The physics is straightforward, the numbers are less so. Simulations suggest kicks up to 5,000 km/s, though most lie below 1,000. Those that exceed a galaxy's escape velocity become true wanderers. Counting them is a matter of inference. Direct detection is almost impossible. A black hole without an accretion disk is dark. We rely on microlensing surveys, where a passing mass briefly brightens a background star. The Macho and Ogle projects have reported a handful of events that could be isolated black holes, but the statistics are thin. From those sparse signals, researchers estimate a number density of roughly 1 per million cubic parsecs in the Milky Way's halo. That sounds sparse, yet the galaxy's volume is enormous, so the total could be in the millions. I plot the trajectories in my notebook, using the measured velocities and the gravitational field of the Milky Way. A rogue's path is a combination of its initial kick and the smooth pull of the galactic potential. Over millions of years, the orbit can become highly eccentric, swinging the hole far above and below the disk. The solar system itself orbits the center at about 220 km/s, completing a circuit every 225 million years. If a rogue's orbit intersects the thin plane where we reside, a close approach becomes possible. The probability, however, is tiny. A simple calculation helps. Take the number density n approximately 10 pc3 and a relative speed v approximately 500 km/s. The encounter cross-section is set by the gravitational focusing radius, roughly square root 2 gm/v2. For a 10 solar mass black hole, that radius is about 0.02 pc. Multiplying n, v, and the cross-section gives an encounter rate of order 10 per year. In other words, a close pass, within a few hundred astronomical units, might happen once in 100 billion years. That is longer than the sun's expected lifetime. I admit it is hard to picture a black hole slipping past the outer Oort cloud without anyone noticing. The gravitational tug on a comet at 50 AU would be minuscule, a whisper against the sun's pull. Only if the hole entered the inner solar system would we see dramatic effects. A sudden perturbation of planetary orbits, perhaps a cascade of comets toward Earth. Yet the odds of such a plunge are vanishingly small. The numbers keep me honest. They do not allow dramatic speculation to take over. Observational limits keep the picture grounded. The Gaia mission, with its precise astrometry, can flag stars whose motions betray an unseen massive companion. So far, no star within a few parsecs shows the wobble that a nearby rogue would cause. Radio surveys for low-frequency bursts have not found the telltale signature of a black hole accreting the tenuous interstellar medium. These null results tighten the upper bound on the local density, pushing the expected encounter rate even lower. There is a subtlety in the calculations that I cannot ignore. The Milky Way is not a static sphere. Its disk, bulge, and halo have different mass distributions. A rogue passing through the dense disk feels a stronger drag, losing kinetic energy and possibly being captured into a bound orbit. Conversely, a hole skimming the halo can retain its speed. The models I run include a simple axisymmetric potential, but the real galaxy has spiral arms, bar resonances, and dark matter clumps. Each adds a small correction, but none changes the order of magnitude result. Encounters are rare. I also note that other galaxies contribute to the background. Intergalactic space is not empty. Black holes can be ejected from one galaxy and wander into another. The local group contains the Milky Way, Andromeda, and several dwarfs. A rogue from Andromeda could, in principle, cross the intergalactic bridge. The relative velocities would be higher, and the probability of intersecting our neighborhood even lower. Still, the possibility is not zero, and it reminds me that our solar system is not an isolated island but part of a larger sea of moving masses. The literature sometimes mentions a dangerous rogue, but the term feels misplaced. Danger implies intent, and a black hole has none. Its influence is purely gravitational, and the only way it could affect Earth is by altering the delicate balance of orbital mechanics. The most plausible indirect effect would be to stir the Oort cloud, nudging a comet onto a sun-grazing trajectory. Even that scenario requires a passage within a few thousand AU, a distance that the statistical models say we will not see in any foreseeable epoch. I keep a separate column for the unknowns. How many black holes are truly isolated, not bound to any star? Do we miss a population that is too low mass to lens efficiently but numerous enough to matter? Are there hidden accretion events that make a rogue briefly luminous, slipping past our surveys? The answers are incomplete, and each new data release reshapes the picture a little. I write these questions down, not as a list of failures, but as a reminder that the universe often keeps its secrets in plain sight. In the end, the numbers tell a quiet story. Rogue black holes drift, some at staggering speeds, but the vastness of space makes a direct encounter with our planetary system exceedingly unlikely. The chance that one will intersect the solar system's path before the sun burns out is, for all practical purposes, negligible. Yet the very fact that such objects exist reminds us that the cosmos is not a static backdrop. It is a restless field of mass and motion. I glance at the latest microlensing alert. A brief brightening lasting a few weeks, consistent with a lens of about 8 solar masses. The data are still being reduced. If it proves to be an isolated black hole, it will add a point to the sparse map we have. Until then, the night sky remains a quiet ledger, each star a potential witness to a passing phantom. A stray photon from a distant quasar, bent ever so slightly by an unseen mass, lands on my detector. The angle of deflection is a fraction of an arcsecond, but it is enough to remind me that somewhere, perhaps a few parsecs away, a rogue black hole is silently tugging at the fabric of space. The idea that a black hole could leak particles feels almost absurd, yet it rests on a few stubborn equations. Stephen Hawking took the familiar picture of an event horizon and nudged quantum mechanics into the mix. Near the horizon, empty space is not empty. It trembles with fleeting pairs of particles that appear and vanish in a heartbeat. If one member of the pair slips past the horizon while its partner escapes, the escapee carries away a tiny amount of energy. That loss, repeated countless times, is what we call Hawking radiation. I find it hard to picture a massive object losing mass grain by grain, but the math does not lie. The rate at which a black hole sheds energy depends inversely on its mass. Smaller holes radiate faster. A stellar mass black hole, a few times the sun's weight, would emit a power comparable to a modest light bulb. Its lifetime, calculated from the radiation formula, stretches far beyond the current age of the universe, about 1068 years. In contrast, a black hole the size of a mountain, say a billion-ton object, would evaporate in a few 100 million years. Even that seems long compared with human history, but it is short on cosmic scales. The energy output of an evaporating micro-black hole would rise sharply as it shrinks, ending in a burst of high-energy particles. Detecting that final flash is a challenge. The background of cosmic rays drowns most signals. Some researchers suggest that a sudden burst could leave a brief imprint on nearby detectors, but no confirmed event exists yet. If a primordial black hole of subplanetary mass were wandering the galaxy, its evaporation could, in theory, be observable. Current surveys of gamma-ray backgrounds place tight limits on how many such objects could exist nearby. Those limits tell us that none are likely to be within a few light-years of Earth. Even if one were, the radiation would spread over a sphere, diluting its intensity by the inverse square law. By the time it reached us, the flux would be minuscule, far below any level that could heat the atmosphere. The notion that a black hole could eat the planet by evaporating is therefore misplaced. What does pose a risk is a black hole that falls into the solar system and begins to accrete matter. That scenario belongs to a different chapter, where gravity, not radiation, does the work. Returning to Hawking's insight, the evaporation process also tells us something about the ultimate fate of black holes. If the universe continues to expand forever, every black hole will eventually fade away, leaving behind a cold, empty space. That picture assumes the laws we use now stay valid for trillions of years, a speculation we can't verify. We don't really know whether quantum gravity will alter the endgame, but the current framework gives a clear timeline. One subtle point often overlooked is that the radiation carries away not just energy, but also information about the black hole's interior. This information paradox sparked decades of debate, nudging theorists toward new ideas about spacetime. Those ideas, while fascinating, do not change the practical estimate of how long a black hole lives. For Earth, the only relevant number is the evaporation time of the black holes that could ever approach us. Even the smallest ones that might have formed in the early universe would need billions of years to reach a dangerous size. Our planet will likely be gone for other reasons long before any such black hole finishes its slow leak. If we ever built a detector sensitive enough to catch a single Hawking photon, it would be a triumph of engineering more than a warning sign. Such a device would have to sit in deep space, shielded from solar wind, and stare at a black hole for centuries. The practical payoff would be a test of quantum field theory in curved spacetime, not a safety alarm. In the lab, physicists mimic horizons with lasers and fluids, watching analog Hawking radiation appear. Those experiments confirm the basic principle without needing an actual astronomical black hole. They also remind us that the phenomenon is rooted in the interplay of geometry and uncertainty, not in any exotic, spooky force. So, does black hole evaporation threaten Earth? The answer, in plain terms, is no. The power emitted by even the most aggressive evaporating hole is far too weak to affect planetary climate or biology. The only conceivable danger would be a black hole of planetary mass that happens to be evaporating right next to us, a situation our surveys have already ruled out. If such a monster existed, its gravity would already dominate the solar system long before its radiation became noticeable. Thus, the radiation itself remains a quiet background process, audible only to the most patient instruments. It is easy to imagine a dramatic finale, a black hole fizzing out like a dying star, but the reality is far subtler. The final moments would be a rapid rise in temperature, a flash of particles, and then nothing. That nothing would be the last whisper of a region that once trapped even light. When we look up at the night sky, the points we label as black holes are, in this sense, slowly losing themselves. Their loss is so slow that, for all practical purposes, they are permanent fixtures of the galaxy. Even the supermassive black hole at the center of our own Milky Way will outlive the Sun by many orders of magnitude. Its Hawking temperature is measured in nanokelvins, far colder than the cosmic microwave background. Because the surrounding universe is hotter, that black hole actually gains more energy than it loses, delaying evaporation indefinitely. Only when the universe cools further will the slow leak begin in earnest. At that distant epoch, any surviving planets will have long since ceased to host life as we know it. So the risk to Earth, now or in the foreseeable future, remains effectively zero. What remains is a quiet curiosity, a reminder that even the most extreme objects obey the same statistical rules that govern a gas in a bottle. If you could stand on the edge of an event horizon with a thermometer, you would read a temperature inversely proportional to the hole's mass. A temperature that, for a solar mass black hole, is a fraction of a degree above absolute zero. That tiny warmth is the signature of Hawking radiation, a whisper in a sea of darkness. I sometimes wonder whether a future civilization might harness that whisper, but any such scheme would require energies far beyond our reach. For now, the best we can do is watch the sky, record the faintest bursts, and let the equations speak. One last detail catches the eye. The most massive black holes radiate at lower temperatures than a cup of coffee, yet they dominate the mass budget of the universe. The idea of a black hole swallowing our planet feels like a science fiction nightmare, but the physics behind it is starkly ordinary. A black hole is simply a mass so compact that its escape speed exceeds the speed of light. From that definition, we can outline three broad pathways by which such an object might affect Earth: a direct capture, a tidal disruption event, and an indirect radiation hazard. Each pathway relies on a different aspect of gravity or high-energy emission, and each carries its own probability. Direct capture is the most literal scenario. If a black hole passed close enough, the gravitational pull would dominate the Sun-Earth system, pulling the planet into a spiraling descent. The distance at which this happens is set by the black hole's Hill sphere, the region where its gravity outweighs the Sun's. For a stellar mass black hole, that sphere is only a few million kilometers across, tiny compared to the distance between the Sun and Earth. A wandering black hole would have to intersect that tiny volume to snag us. I find it hard to picture a rogue black hole wandering through the Milky Way with a trajectory that lines up so precisely. The odds are astronomically low, and the sky surveys we run have not spotted any such intruder on a collision course. Even if a black hole never reaches the exact point of capture, it can still wreak havoc through tidal forces. When a massive object passes within a few astronomical units, its differential gravity can stretch and compress any nearby body, a tidal disruption event. In the case of a star, the result is a spectacular flare of gas. For Earth, the effect would be far less luminous but potentially catastrophic. The planet would experience a gradual elongation, the oceans sloshing in response to the altered potential. The stress on tectonic plates could trigger widespread earthquakes and volcanic eruptions. The calculations show that a black hole would need to pass within roughly 100,000 kilometers to produce measurable tides on Earth. That distance is still far smaller than the typical separation between stars, making the event improbable, yet not impossible in a galaxy that has lived for billions of years. High-energy jets provide a more indirect but perhaps more realistic danger. When matter falls toward a black hole, it forms an accretion disk that heats to extreme temperatures. Magnetic fields can channel a portion of that energy into narrow, relativistic jets that shoot out along the rotation axis. Those jets are composed of particles moving near light speed, and they can travel thousands of light years before dissipating. If a jet were to intersect Earth, it would bathe the atmosphere in high-energy photons and particles, a phenomenon sometimes called a gamma-ray burst if the jet points directly at us. The energy deposited would ionize the upper atmosphere, destroy ozone, and allow more ultraviolet radiation to reach the surface. Estimates place the safe distance for a typical jet at several kiloparsecs, far beyond the nearest known black holes. Still, a black hole that happens to be aligned with Earth and is actively feeding could, in principle, deliver a brief but intense pulse of radiation. Radiation hazards do not stop at jets. The very presence of a black hole can alter the local flux of cosmic ray-like particles. As a black hole moves through interstellar gas, it can accelerate particles in its wake, creating a halo of high-energy protons and electrons. Those particles diffuse through the magnetic field of the galaxy and eventually reach the solar system. If the flux were to increase by an order of magnitude, the background radiation dose at the surface would rise measurably. The effect would be gradual, not a sudden flash, and it would depend on the black hole's speed and the density of the surrounding medium. Models suggest that a black hole would need to be within a few parsecs and moving relatively slowly to boost the particle flux appreciably. That configuration is rare, but the galaxy does contain a handful of black holes in the solar neighborhood, so the possibility cannot be dismissed outright. When we compare these black hole threats to other astrophysical hazards, such as supernovae, solar flares, or asteroid impacts, the picture changes. A nearby supernova can outshine an entire galaxy for weeks and flood Earth with deadly radiation. A solar superflare can strip satellites and disrupt power grids. An asteroid impact can excavate a crater the size of a city in seconds. In terms of sheer probability, an asteroid strike remains the most likely of the lot, while a direct black hole capture sits at the bottom of the list. The jet and radiation scenarios occupy a middle ground. They are unlikely, but they are not ruled out by current observations. Our ability to assess these risks rests on a combination of observation and theory. Telescopes that monitor the sky for transient events have cataloged dozens of tidal disruption flares and gamma-ray bursts, giving us a statistical baseline. Gravitational wave detectors have begun to reveal the population of stellar mass black holes wandering the galaxy. Yet we don't really know how many quiet, non-accreting black holes hide in the dark between the stars. The surveys are improving, but the data are still sparse enough that any estimate carries a large margin of error. Even with the best models, some aspects remain vague. For example, the exact mechanism that launches jets from an accretion disk is still debated. I sometimes struggle to explain why magnetic fields should align so perfectly to produce a narrow beam rather than a diffuse outflow. The uncertainty does not invalidate the risk, but it does make the precise calculation of a jet's reach difficult. Likewise, the interaction between a passing black hole's wake and the galactic magnetic field involves plasma physics that we can only simulate on a computer. Those simulations give us a sense of scale, but they cannot capture every nuance of a real system. One might wonder whether any of these scenarios could happen soon enough to matter for humanity's planning. The answer is, in most cases, no. The nearest known black hole, V616 Monocerotes, sits about 3,000 light-years away and is not actively feeding. Its jets, if any, are pointed away from us. The closest black hole candidate that could, in theory, produce a jet aimed at Earth is still beyond the range where its radiation would be dangerous. In other words, the sky is quiet enough that we can focus on more immediate concerns. Nevertheless, the exercise of categorizing black hole threats reminds us how delicate the balance of forces is around our planet. A small change in distance, a different orientation, a burst of accretion, any of those could shift a harmless neighbor into a source of danger. The universe does not arrange its objects for our convenience, and the occasional outlier may still appear. A final, perhaps trivial, observation. The nearest known black hole's mass is roughly 6 times that of our Sun, yet its event horizon is only about 20 kilometers across, about the size of a small city. That tiny sphere of darkness, floating in the void, holds the potential to influence a world billions of kilometers away. The probability of a black hole ever reaching us is, in practice, a number that lives far beyond everyday intuition. When we write it down, we start with the catalog of known black holes, about a dozen million stellar remnants scattered through the Milky Way, plus the central supermassive object that weighs millions of suns. From that inventory, we can ask, how many of those wanderers could ever come close enough to disturb the solar system? Statistical risk assessment begins with a simple density calculation. The galactic disk spans roughly 100,000 light-years, its thickness a few hundred. If we spread a few million black holes uniformly, the average separation is on the order of 1,000 light-years. That spacing already suggests a collision is unlikely, but the galaxy is not static. Stars and black holes drift under the influence of the overall gravitational field, and their orbits can shift over billions of years. Timescales of galactic dynamics are long enough that we must think in gigayears rather than centuries. The Sun completes one orbit around the galactic center every 225 million years, and the same holds for most objects in the thin disk. A black hole that happens to be on a similar orbit will, on average, stay at roughly the same radius, never closing the gap to the Sun by more than a few tens of light years. Only when a perturbation, perhaps a close encounter with a massive molecular cloud, throws an object onto an eccentric path does the chance of a near-miss increase. To put those odds in perspective, we compare them with other high-energy hazards. Supernovae within a few hundred light-years are known to sterilize planetary atmospheres, and gamma-ray bursts, though rarer, can deliver lethal radiation across the galaxy. The estimated rate of a supernova threatening Earth is about 1 per half billion years. Gamma-ray bursts are perhaps an order of magnitude less frequent. Black holes, by contrast, lack the explosive outburst that makes a supernova dangerous, and their influence is limited to tidal forces and accretion radiation, both of which require a very close approach. The tidal sphere of a stellar mass black hole, the distance at which its gravity would start to pull noticeably on the Earth, is only a few hundred kilometers. That is minuscule compared to the interstellar distances we are dealing with. Even the supermassive black hole at the center, Sagittarius A*, exerts a measurable pull only within a few light years. The Earth would have to wander into that sphere for any direct gravitational danger, and the odds of that happening are vanishingly small. Uncertainties in the models dominate the final numbers. Our census of black holes is incomplete. Many lurk unseen because they are not actively accreting matter. Their masses are often inferred from indirect measurements, and their velocities are known only for a fraction of the population. Moreover, the Milky Way's spiral arms are not static, and the bar structure can shepherd objects inward over long periods. I find it hard to picture how these slow, collective motions translate into a precise probability for a single planet. Future observational improvements promise to tighten the bounds. The next generation of astrometric surveys will map the motions of faint objects with micro-arcsecond precision, turning unknown wanderers into cataloged points. Gravitational wave detectors, now sensitive to mergers of stellar mass black holes, will also reveal the birth rate of new remnants, giving a better handle on how many fresh black holes are added each million years. With that data, we can refine the statistical model from a rough estimate to something that feels less like guesswork. Putting the pieces together, the most likely black hole that could affect Earth would be a stellar mass remnant passing within a few thousand astronomical units, a distance still far enough that only a faint X-ray glow would be detectable. Even that scenario would require a perturbation that nudges the black hole onto a trajectory intersecting the solar system's neighborhood. The probability of such a perturbation, given current orbital distributions, is on the order of 1 in 10 million per 100 million years. In other words, the expected waiting time stretches beyond the current age of the Sun. If we broaden the view to include indirect effects, say, a black hole that captures a passing star and launches a jet of high-energy particles, then the risk envelope expands slightly. Yet those jets are highly collimated, and the chance that one would intersect Earth's orbit is again minuscule. Compared with the more frequent supernova threat, the black hole hazard sits at the far end of the risk spectrum. All of this rests on the assumption that the Milky Way will remain largely unchanged for the next few billion years. We do not really know how the galaxy will respond to the eventual merger with Andromeda, an event that will scramble stellar orbits on a scale dwarfing any current motion. That future collision could fling black holes into new paths, but the timescale for the merger, several billion years, means any resulting danger would arrive long after the Sun has exhausted its fuel. In the end, the numbers tell a quiet story. Black holes are abundant, but their lethal reach is razor-thin, and the galaxy's slow dance keeps them at arm's length. The most concrete observation we have right now is the faint radio whisper from Sagittarius A* that tells us the central monster is currently dormant. its appetite satisfied by a thin trickle of gas. The silence of that signal is, oddly, the most telling detail. I keep a notebook beside the telescope, its metal cold in the night air. The instrument points toward the black hole at the galaxy's heart, gathering photons that have survived a long, warped trek. Space-based observatories now scan the sky continuously, their mirrors free from Earth's turbulent atmosphere. They record subtle flickers that hint at a merger or an unexpected flare. Early warning networks stitch together data from radio dishes, X-ray satellites, and ground-based interferometers. When a signal crosses a preset threshold, an alert flashes on a console, a soft beep cutting through the lab's hum. I find it hard to picture how a ripple in spacetime could travel millions of kilometers and still be caught by our detectors. The math feels thin, the reality feels heavier. Some scientists propose placing a swarm of small probes near a threatening black hole, hoping to alter its accretion flow. The idea sounds like science fiction, yet the calculations are laid out on a whiteboard, each line a careful estimate. Others suggest using focused laser bursts to push away infalling gas, reducing the black hole's growth rate. The laser would need power comparable to a small star, a detail that makes the plan feel distant. I don't really know whether any of these schemes could ever be built. The engineering challenges are immense, and the timeline stretches far beyond a single generation. Even if we could slow a black hole, the question remains: why intervene at all? Humanity has survived ice ages, asteroid impacts, and pandemics. Each crisis left a mark on our culture, a reminder of our place in a vast, indifferent expanse. Our current monitoring systems rely on redundancy. If one satellite fails, another picks up the slack, its antenna humming in a different orbit. The network's resilience is a product of cautious design, not optimism. The data streams flow into servers that store terabytes of information, their hard drives humming like distant engines. Researchers sift through the logs, looking for patterns that could precede a dangerous outburst. Sometimes the software flags a false alarm, a solar flare masquerading as a black hole signal. The team pauses, re-examines the waveform, and sighs in relief when the source is identified. There is a quiet humility in that moment, a recognition that our tools are imperfect. We learn to trust the process, not the outcome. Public outreach programs now include live feeds of the observatories, allowing anyone with an internet connection to watch a pixelated image of a distant horizon. The view is grainy, but it carries a weight that feels almost personal. I admit I sometimes wonder whether the public's fascination with black holes distracts from more immediate concerns. Yet the fascination also fuels funding, which keeps the detectors running. The philosophical side of the discussion surfaces when we ask why we bother cataloging objects that will outlive us by billions of years. The answer, perhaps, lies in a simple desire to know what surrounds us. Our species has always built tools to extend perception: telescopes, microscopes, spectrometers. Each new instrument adds a layer of detail, a new texture to the picture of reality. When a new transient event is recorded, the team gathers around a screen, the glow illuminating tired faces. The event may be a distant star being torn apart, or a sudden burst from a hidden black hole. We compare the timing, the energy, the spectrum, looking for clues that fit into existing models. If the numbers don't match, we note the discrepancy and move on. I find it hard to picture the exact moment a black hole's event horizon would intersect with Earth's orbit. The calculations involve distances that make ordinary scales feel meaningless. Some theoretical papers explore the notion of black hole shielding using exotic matter, a substance that could, in principle, bend gravity. The concept remains speculative, anchored more in mathematics than in laboratory proof. Even if such matter existed, the amount required would be comparable to a mountain's mass, a detail that keeps the idea in the realm of thought experiments. Our current mitigation concepts therefore focus